Now we are going to introduce one extremely important theorem that is due to Levy, the famous probabilist and mathematician in the last century, rather in the first half of the last century and first half of the last century. He is extremely brilliant in developing many results in probability theory, especially related to the convergence in probability or convergence almost surely. As we have already seen that it is extremely important and interesting to know what is the relation between different types of convergences, because we know that convergence in probability is one type of convergence. There is another convergence which is called convergence in distribution. Another type of convergence is convergence almost surely, and so on. There is also LP convergence and so on. This Levys theorem deals with the relation between this almost sure convergence and convergence in probability. So which one implies the other, whether convergence in probability implies almost surely or the other way around. This question will be answered by Levys theorem. But before stating Levys theorem, we will discuss another important inequality that is again due to Levy, which will be useful in proving this Levys theorem that deals with the relationship between, or when under what condition one converges implies the other, and the converse. So we are going to discuss Levys inequality first and then Levys theorem in great detail, because we need to understand the proof, the technique of the proof, that is also extremely important. So we are going to state and prove Levys theorem, but before stating, rather proving Levys theorem, we have to introduce some concept and also another inequality. So before that, let me first introduce with Levy. He is a very famous mathematician and probabilist in the last century and did significant contribution in the theory of probability. Levys theorem is basically considered a milestone in probability theory. It's really a pioneering work which you will immediately realize after when you see the statement and the proof of this theorem. But this theorem depends on an inequality which is called a maximal inequality, that is again due to Levy. But before that, we should discuss a few definitions and observations on some important but obvious properties of random variables. Now we have some idea about the random variables and independence and all sorts of things. We are going to do a quick recap and just try to observe some important but very obvious properties of these random variables, which will be useful in proving this inequality as well as the theorem due to Levy. First one is that suppose x is a random variable, then there exists at least one finite number mu of x. We call this mu x as the median of x, such that we define mu x such that probability x less than equals to mu x is greater than equals to half, which is less than equals to probability x greater than equals to mu x. Now if x has a distribution function, since x is a random variable, it should have a distribution function. If this distribution function is capital F, then capital F of mu x minus is less than equals to half less than equals to capital F of mu x. Clearly from this definition, it is very clear that median may not be unique. That really doesn't matter too much in the theory of probability. Second observation is, some facts are a random variable x is said to be symmetric. In this case, let me consider in its generality that or without loss of generality that it is symmetric about 0 if probability of minus x less than lambda equals to probability a capital X greater than minus lambda, for lambda is finite, that is minus infinity less than lambda less than infinity. This immediately implies that capital X and minus x has the same distribution function. So we call a random variable x to be symmetric about 0 if capital X and minus of capital X has the same distribution function. Now if 0 is the median of x, then x is symmetric about 0, that is by the definition of median, which means that probability x less than equals to 0 is greater than equals to half, which is less than equals to 0 of probability x greater than equals to 0. We have already seen this next result or next statement in while discussing characteristic function, that is, if x1 and x2 are independent random variables that are symmetric about 0, then so is x1 plus x2. That means x1 plus x2 is also symmetric about 0. The proof is very simple. Characteristic function of x1 is phi1t, which is expectation of e to the power t x1, and phi2t is the characteristic function of x2, which is its expectation of e to the power I t x2. They are both real because they are both symmetric about 0. Then if we calculate the characteristic function of x1 plus x2, this would be phi1t into phi2t, because x1 and x2 are independent. Now since phi1t and phi2t both are real, naturally product of these two functions will also be real, and hence this is symmetric. So the proof is very trivial using characteristic function. But these are few observations. Now with this, let me state the famous Levys inequality. I will tell you one important feature of this inequality just after stating this inequality. Suppose x1, x2, xn are independent random variables, and we define Sn as summation of xi I equals to 1 to n. Then for every epsilon greater than 0, it might be however small, we have two inequalities, one with respect to sk, another with respect to modulus of sk. That means probability maximum over k lies between 1 and n, sk minus mu of sk minus sn. This entire quantity is greater than equals to epsilon. Probability of this event is less than equals to twice probability of sn greater than equals to epsilon. The same kind of result holds when you replace this sk minus mu of sk minus sn by the modulus of this function. That means probability of maximum 1 less than equals to k less than equals to n, modulus of sk minus mu of sk minus sn greater than equals to epsilon less than equals to twice probability modulus of sn greater than equals to epsilon. Now mu is, we have already mentioned that mu y is the median of y. Now this inequality is extremely interesting. Obviously this is important, but it is also very interesting because this does not involve any moment of the distribution of xi's or sn. So this is a very important feature of this Levys inequality, that it does not involve any moment. So it is without the existence of any moment of the distributions. Now if we consider, instead of x1, x2, xn, they are all independent random variables, but again if we consider that they are also symmetric random variables, then for every epsilon greater than 0, we can immediately say that probability of maximum of xk, k lies between 1 and n greater than equals to epsilon, that is less than equals to twice probability sn greater than equals to epsilon, and similarly probability of maximum 1 less than equals to k less than equals to n modulus of sk greater than equals to epsilon less than equals to probability modulus of Sn greater than equals to epsilon. Another interesting feature of this inequalities is that the same kind of inequality holds whenever we replace the random variable or the sum of random variables by its modulus or modulus of the sum of random variables. So these are very interesting features of Levys inequality. Let us try to prove this inequality. First, set S naught equals to 0 and let me define capital T as the first k when k lies between 1 and n such that sk minus mu of sk minus sn greater than equals to epsilon and n plus 1 otherwise. So I am defining T in terms of sk minus mu of sk minus sn greater than equals to epsilon, which actually takes part in the inequality statement. Now let us also define an event by ak. Ak is the event which is mu k sk minus sn greater than equals to sk minus sn for k lies between 1 and n. Then it is clear that by the definition of median we can immediately write that probability of ak is greater than equals to half. Now let us note this t equals to k. Now t equals to k is basically belonging to the sigma field generated by x1, x2, xk, and hence ak also belong to the same sigma field generated by xk plus 1 up to xn, and Sn greater than equals to epsilon that contains union of k equals to 1 to n ak intersection t equals to k, and ak and t equals to k are independent because this ak is defined for xk plus 1 up to xn and t equals to k is defined up to this k, or rather up to xk, and x1, x2, xk, xk plus 1, xn, they are all independent. So naturally ak and t equals to k, these two events are also independent. Now what is probability Sn greater than equals to epsilon? Now probability Sn greater than equals to epsilon is naturally greater than equals to summation j equals to 1 to n ak, probability of ak intersection t equals to k, because we know that the event Sn greater than equals to epsilon contains this union of ak intersection t equals to k. So just by monotonicity property of probability, probability of Sn greater than equals to epsilon is greater than equals to summation j equals to 1 to n probability of ak intersection t equals to k. Now since ak and t equals to k event, these two events are independent, we can immediately write probability of ak into probability of t equals to k sum over k equals to 1 to n. Now again we know that probability of ak is greater than equals to half, so immediately we can replace probability of ak by half, so that there will be a greater than equals to sign half into summation probability t equals to k equals to 1 to n, which indicates that this is equals to probability 1 less than equals to t less than equals to n. Now what is t? What is this event? Probability 1 less than equals to t less than equals to n. This is nothing but probability of maximum of 1 less than equals to k less than equals to n sk minus mu of sk minus sn greater than equals to epsilon. This is by the definition of t. The way we defined t immediately gives us this inequality basically. So that is the beauty of this proof. The way we define t, that immediately implies the independence of ak and t, which in turn defines another event with respect to t, which in turn gives the final inequality. So from here we get the Levys inequality. Now if we consider, or rather replace xk by minus xk, and note that probability of x less than equals to mu x greater than equals to half less than equals to probability x greater than equals to mu x, because mu x is the median, and naturally mu of minus x equals to minus of mu x, then we apply this same inequality that is given in A of the inequality statement of the inequality, and we just add them. We will get the second statement of Paul Levy's inequality, which is in terms of modulus of sk minus mu of sk minus sn. Thus we have proved this extremely important and extremely famous inequality due to Levy. Now let us state Levy's theorem way back. This is actually established way back in 1937. Suppose xn's are independent random variables. The theorem is very simple. It relates almost shear convergence and convergence in probability. So if xn is a sequence of random variables that are independent, then summation xn n equals to 1 to infinity converges almost surely if and only if summation xn converges in probability. This is a very simple statement but extremely important again. To prove Levy's theorem, we actually need another lemma along with Levy's inequality. This lemma is if xn converges to x in probability, then probability modulus of xn minus xm greater than equals to epsilon is less than epsilon whenever m greater than n greater than equals to n naught. So this actually comes directly from the definition of convergence in probability and very simple to prove. Now, to prove Levy's theorem, if we consider the one part, that is converges almost surely, this will immediately imply convergence in probability. We have actually proved it long back, but almost sure convergence always imply convergence in probability. So necessity part is obvious, we don't need to bother about it. Now comes the sufficient part, sufficiency part. Now here we have assumed that convergence in probability holds. Now to show that converges almost surely, that means to show Sn converges almost surely, it is enough to show that the partial sum Sn converges in probability implies Sn converges almost surely. So let us first define Sm, n by double suffixes as Sn minus Sm. Now by the previous lemma, for every epsilon greater than 0, there exists an integer m0 such that whenever n greater than m greater than equals to m0, probability of modulus of Sn minus Sm, which is nothing but Smn greater than epsilon, is less than epsilon. This is just by the previous lemma, because we have assumed here that convergence in probability holds, which immediately implies that since probability of modulus of Smn greater than epsilon is less than epsilon, this probability is extremely small, this immediately implies that modulus of mu of Smn is less than epsilon for n greater than m greater than equals to m0. Now we just use Levys inequality directly. We have for j greater than m greater than equals to m0, we have probability maximum over m less than n less than equals to j modulus of Sm comma n greater than 2 epsilon. Just for the sake of mathematical simplicity, we have taken this 2 epsilon, which is equals to probability maximum over m less than n less than equals to j modulus of Sm comma n greater than 2 epsilon comma maximum of m less than n less than equals to j modulus of mu of Smn less than epsilon, which is less than equals to probability of maximum m less than n less than equals to j modulus of Smn minus mu of Smn minus Smj modulus of that greater than epsilon. Now again, this is less than equals to by Levys inequality, less than equals to twice probability modulus of Smj greater than epsilon, which is less than equals to 2 epsilon, because this inequality probability of modulus of Sm comma j greater than epsilon is less than epsilon. So this becomes less than equals to twice epsilon. Now if we let j to go to infinity, if m greater than equals to m0, then probability of supremum over n greater than m sup of Sm comma n greater than epsilon, that is less than equals to 2 epsilon, which immediately says that basically this is the lim sup, so which basically says that Sn converges to S almost surely. Let us consider this almost sure convergence to a random variable S, which we call actually S. So this means that convergence in probability implies convergence in almost surely, provided that for this summation of xi. So this is the famous Levys inequality, and this is the famous Levys theorem that relates convergence in almost surely and convergence in probability. So we have discussed Levys inequality, and then we have proved rigorously Levys theorem. One important feature, as we have already mentioned probably during the derivation of the proof, that Levys inequality doesn't require any assumption regarding the moments of a distribution, which is extremely important, because in most of the situations, in many results in probability theory, we usually assume moments up to certain order should exist in order to be the validity of to check the validity of the result. But in Levys inequality, which is actually proved way back in the first half of in the last century, even then he proved this extremely powerful inequality, and hence the theorem, without the assumption of any moment. Now, there is some assumption of the moment in case of theorem, Levy's theorem, which deals with the relation between almost sure convergence and convergence in probability. That means one implies the other under certain conditions. But Levys inequality is completely independent of any kind of moment, which is extremely very powerful result, and that can be used in any area in probability theory. So Levy's theorem also gives us a direction that and how one can think of this relation between these two types of convergence and how one can develop some kind of results and how to prove these results. So this Levy's theorem has, again, I should emphasize that these two, one inequality and another theorem, is extremely powerful in the entire probability theory.